Now that we have a velocity profile for fully developed laminar flow, we can use that to calculate out a bunch of different things within the system a little more exactly than we were able to do before. Well, the first is, let's calculate out the velocity of the pipe. So we know the velocity is going to be the Q over A, so the capacity over the area. And this velocity that we're calculating out, even though that we do not typically write it out, that's the average velocity, because that's what we need for calculating our equations. So now if we go back up and we look at our equation here, if we plotted that, that's a parabola. So from geometry, we know that the average value on a parabola is going to be half the max. So we can go U max divided by 2 will give us what our average velocity in the pipe is. So we have what our we have what our maximum velocity is from here. So we can plug our dp dx into that and calculate it out. And so for average velocity, what we're going to get is delta p plus gamma delta z divided by L. So there's our dp dx term. R squared over 8 mu. Wait a minute, it was 4 mu up here. Well, we've got that 2. So let's we'll box that out because I know students like their boxes. So that's our average velocity. How do we calculate out flow rate? We want to do something else. So Q. What is Q? Well, technically Q is the integration of all the speed over the area to find out how much is flowing through. Or we've got over here our average velocity times our area will also give us our Q. So that would be the average times pi r squared. So if we do either of those, what we're going to end up with is pi r to the 4th over 8 mu times our dp dx. dp plus gamma dz over L. So that's a way to calculate out Q. Next, we'll take a look at shear stress at the wall. Going back to our equation for shear stress, we plug our newly found velocity profile for laminar flow. We end up getting R over 2 times delta P plus gamma delta Z over L. Now this equation here is great because it allows us to do something that we haven't been able to do yet, which is easily calculate out shear stress. Because I can measure the pressure difference, I can measure the height difference. And given that with all these other numbers, because I can measure the radius of the pipe, I can know the length of the pipe, I can actually calculate out what the shear stress of the wall is for laminar flow. So now if I take this and I go back to my HF equation for laminar flow, I can actually write out an expression for it in things that are easy to measure. So once I plug that in, I will have 32 mu, so my viscosity of my fluid, L times the average velocity, divided by gamma d squared, where d is the diameter of the pipe. Now if I wanted this in flow rate, I can do that, because I just basically take that velocity, replace that velocity by Q times A, rebalance all the numbers, and that'll also be 128 mu LQ divided by rho pi d to the 4th. And so that's great, because now I have a way to calculate out head loss due to friction in terms of everything that I can measure easily. Viscosity of the fluid's not a problem, length of the pipe's not a problem, diameter of the pipe's not a problem, specific weight of the fluid's not a problem, calculating out velocity or flow rate, all not a problem. So if I take this and I plug this back into my Darcy equation, my Darcy-Weisbach equation, so remember Darcy-Weisbach equations, HF is FL over D, V squared over 2G. So if I take this, plug all of this stuff in for HF in the Darcy-Weisbach equation, I can directly calculate out F for laminar flow is just going to be 64 over the Reynolds number based on diameter for laminar flow only. This is only laminar flow. I have to stress that immensely. So only when the Reynolds number based on diameter is less than 2300. But we can directly calculate out the Darcy friction factor just knowing the Reynolds number.